Okay, so you're asked to derive the equation of motion for a simple pendulum, and all that means is that you don't have to worry about friction or any sort of other things like that. The rope is not changing lengths, it's just a simple pendulum. Okay, so this is your simple pendulum, and it's just a string, and we're not going to be worried really about the mass of the string, but instead just the mass of the ball. And we know that it's, how pendulums go. They go up, and then they go down, right? And obviously the radius is fixed, right? The rope is not changing lengths. It's just going up and down. So the only thing that's really changing is this length, theta. However, you do know that you do have some weight, right? You do have weight of the mass pulling down. And weight is equal to mass times gravity, right? So this is really all that's happening. But to analyze this, we should establish a well-known fact, and it's not that crazy to say that, hey, this is a length L. Instead of writing big L, I'll write little l, just for, you'll see why in a second. Okay, so if all that's true, and you want to find the equation of motion, you want to find some sort of acceleration, velocity, or position equation. That's the equation of motion, right? I'm going to tell you that there's a way to go about this easier than using Newtonian mechanics. Where Newtonian mechanics you would try to find the x and y axes and do all that type of stuff. And that would be a lot harder in my opinion. Instead, if we use these two facts here, that Lagrangian is equal to the kinetic energy, which I'm going to call K, minus the potential energy, which I'm going to call P. Right? K minus P is the kinetic minus the potential energy. That's the Lagrangian. And then if we use the Euler-Lagrange equation, which is the partial with respect to time, for the partial derivative of the Lagrangian, for the coordinates change in position. Now, think about the coordinate. What coordinate are we using? Is L our coordinate? Or is theta our coordinate? Well, theta is our main variable coordinate here. Okay. Minus d Lagrangian d theta equal to 0. So these two equations can tell us the equation of motion. You're going to see in a very quick second how I'm going to be able to do all that stuff. Okay, but first let's just define what kinetic and potential energy are. So K is equal to 1/2 mv squared, right? Okay, well that's true. And we're like, yes, I know that. Well, mass is mass, so m is m. Well, what's velocity? What is the velocity? Okay, well, we should note that, look at the path of this real quick. See how it's scrolling up in this arc? Well then, if we know that arc length is equal to some distance s equal to theta times the radius, and the radius in our case is L, right? The radius is the length. That s equals theta times L is the arc length equation. So s equals theta L. If we know that s is the position of the mass at all times, then s dot, right, the derivative of that with respect to time, ds dt, or s dot, whatever you want to call it, is going to be the velocity. So we're going to write it mass over 2. We're going to have s dot squared. And that's the same thing as what? M over 2. And then it's going to become L theta dot squared. Because length doesn't change, but if you take the derivative of that, the only thing that is changing is theta dot. So that's the kinetic energy equation. And I'm going to put a nice little box around it here, because this will be important for us to use. Okay. Now, there's a little bit more that we still have to do, right? There's always a lot that we got to do. But what is the potential energy? Well, the potential energy is equal to the mass times gravity times height. Right? Okay. Now, if we look at this diagram, right, there is a changing height. It's going up, right? So if I cut it off right here, you can see that there's this triangle, right? And that there's some change in height. Okay? And then you ask yourself, well, how do I know what the change in height is? Okay, well, you know that this height right here is what? And you know that, sorry, let me draw this diagram here. More space, I won't use you guys. So you have this situation, right? And this is what it's going to look like. Right, here's your mass, and it's swinging up, right? So you have these two lengths, and this is your change in height. So you have this total length, right? And we call this L, and we call this theta. And then we also have this other length, right? And right here is your change in height. Now, if we know how triangles work, we could see that, let's just cut that string for a second, like that, and write it like this. Well, then we know that the height over here is just what L cosine theta. Right? Look at that. See, it's L cosine theta. Now what about this one? Right? Well, that's just going to be L, right? The length when the string, right? So at that moment the string is pulling it up, right? It's going up like this. But then if we were to go back to normal, right? And just pretend that the string like goes back down to the bottom, right? It's coming back down and now it's just here. So it's the original length of the string minus the length of the string. Okay, let me say that again. The length of the string is not changing at all, right? It's just moving up. And if it moves up, then we have to use cosine theta to describe the height of where the mass is. That's the important part. But at the bottom, then we can just describe where its mass is just using the pure length. Okay. So in other words, change in height is equal to what? It's L minus L cosine theta. That's all it is. That's it, right there. So if we go back to potential energy, right? We could see that potential energy is equal to mass times gravity. And I'm going to factor out a L here. 1 minus cosine theta. This is our potential energy. So this is our kinetic energy and our potential energy. Put a box around this guy. So we're actually like nearly done with the problem now since we can define those two things. So if we subtract them, let's find our Lagrangian. Okay. So we should note that the Lagrangian is going to equal to the kinetic energy minus the potential energy, which would be m over 2, and then it's going to be theta dot, right, L times theta dot squared minus now this potential energy, which is mgl 1 minus cosine theta. So this is our Lagrangian. And we could see that we need to, this equation doesn't give us that much, but this equation tells us a lot more. So now we got to find these partial derivatives. So we can break it into parts real quick. We can find this partial derivative first and then find this partial derivative. I think we should start with finding this partial derivative. Okay. So we want to find the partial of the Lagrangian with respect to theta dot. Okay, so theta dot is what we're differentiating with respect to. So as you can see here, the right hand side for, right here, the derivative with respect to theta dot 0. However, if we take the derivative of this with respect to theta dot, what do we get? That's a big question. Okay, so let's do that. Okay, so if we take, like I said, we're just taking the derivative of this whole thing with respect to theta dot, but we see that this is the only term that has a theta dot in it. So what happens? We get 2 times m over 2, and then remember that this is L theta dot squared, so then it's just going to become L theta dot, right? And you know how, the rule works here, is then we have to take the derivative of the inner, and we just get L, right? So basically, you see the 2's can go away, and we get m L squared theta dot. Another way to do it, you can think about it is, you could just write m over 2 L squared theta dot squared, and then you'd see that that derivative would just turn into what? M L squared theta dot. So it's the same thing. I just wanted to show you how to take derivatives right there. Maybe that was a waste of your time. It can get confusing with the theta dot, right? So don't mess that up. Because if you do mess it up, then everything else has to be wrong, right? Okay, well this is the Lagrangian with respect to theta dot. So it's this derivative. Now we want to take its time derivative, right? Because that's what the equation says to do. So if we take its time derivative for m L squared theta dot, the only thing that changes with time is the radius. So then what do we get? We get ml squared theta double dot. Okay. So we're nearly done. The last thing we need to do is take the Lagrangian's derivative with respect to theta. So taking this guy with respect to theta only, and then you'd see that this is the only term with a regular theta in it. Okay? So what do you get? So you get d Lagrangian, that's r for some reason, Lagrangian, d theta is going to equal to this guy's derivative. Again, the only thing that has a theta in here is this negative cosine theta, and you take the derivative of negative cosine theta, well, take the derivative of this thing right here, what do you get? You get positive sine theta. So then you get negative mgl sine theta. And remember that there's a negative in front of this equation. I mean, in front of this derivative right here for this equation, and then we see that there's a negative here, but we just had the positive. So what we can do here is just write negative Lagrangian d theta is equal to mgl sine theta. Okay, so I'll just move the negatives around there. So we have everything we need, right? Going back up again, we found this guy, we found this guy, and we know that's all equal to 0. So let's write that down. Okay, let me show you guys. Oh, where's my mouse? Okay, right here. This guy right here, and this guy right here is the only pieces of information we care about. So we get ml squared theta double dot minus mgl sine theta. This is equal to 0. What can you see that can go away? We can see that we can factor out the masses, right? And they go away. And then you can see that this is a negative here, so we can put it on the other side. So then we're going to get L squared theta double dot is equal to GL sine theta. And then if we just put theta double dot by itself, because that's what we want to do, because that would make sense because it's the equation of motion, right? And we can see that if we divide by L squared, we're just going to get G over L sine theta. And this is your answer. I mean, this is the equation of motion for a simple pendulum. Right? This is all you need to do. What you could do is you could integrate, with respect to time, and then you could see, you can get another equation, and then if you could do it again, you get another equation for position, right? But we'll just leave it like this because this is the most general basic form, and this is all we need. We're done here. Okay, I hope that helped for learning how pendulums work. I'm going to zoom out here and show you guys everything. Do a little recap. So we have this pendulum. It has a fixed length L, and its angle is changing as the pendulum swings up. As it swings up, it has to have a change in height. Therefore, it must have a potential energy. And also note that it is moving, so it has a kinetic energy. Therefore, we can use Lagrangian mechanics. We can use the Lagrangian equation, and then we can use the Euler-Lagrange equation to find our actual result. The hardest part about this whole thing was knowing how to do the trigonometry right here. Okay. And then the rest is just taking, just straightforward derivatives of the kinetic and potential energy, and you get this at the end. So, that's it. Have a good day.